Hello everyone, and welcome to this video titled The Limit Laws. In this video, I'm going to be taking you through a preview version of an assignment at Knewton Alta that is also titled The Limit Laws. So please understand that this is a preview of the assignment. So that means that the questions that I go over in this particular video may not be exactly the same questions that you see when you work on it as a student, but the objectives are the same and the way you would go about working through these problems should be very similar. So I'm hoping these help. So here we are at the Knewton Alta site. Now you won't be seeing the word preview, or you'll just see the title of the homework. So in this particular course, this is section 2.3 homework, the limit laws. And in the upper right hand corner, you'll see your mastery bar that tells you how far along in the assignment you've gotten. Next to that, your activity log, which shows you all the objectives of the assignment. Okay, so this particular assignment has 8 objectives broken up into 4 sections. So at the moment I'm in the one titled Evaluating Limits with the Limit Laws. And there's only one objective in this section, right? So I'll be getting 4 or 5 questions in a row on this one objective, and then it will move me to one of the other 3 sections with the several other objectives. Now, if I wished, I could start a different section. Right, notice these start buttons here, and then it'll keep me in that section's objectives until I'm done with them, unless I want to start something else. But I'm not going to be doing that, just letting you know that that's an option for this particular course. So then you have the current objective, right? So it's use the limit laws to evaluate the limit of a function. A question related to that objective. This one's a fill in the blank one. And at the bottom of every question, you'll see a feedback button. So if there are any typographical errors or anything that you see as incorrect with either the question or the answer explanations, you can send feedback directly to Knewton's support, and hopefully someone from their team will get back to you shortly and fix the problem, help you fix the issue. Now this instructor cheat button, right, you will not have this, of course, as a student. This is for instructors only, and I'm not going to be using it here in the video. But you will see a more instruction button. So if you're ever working on a question in a particular objective and you don't remember the material very well, need some extra help, click on this, and some reading to do, maybe some videos to watch, or both related to that particular objective will come up, and then you can work on a question while that instruction is available and get through the assignment that way. All right, so this first objective, use the limit laws to evaluate the limit of a function. Right, so I'll just be listing the laws as I use them. I'm not going to write all of them out. And what you're going to notice is for most of these limit laws, when you're evaluating the limit of some expression, as say x approaches a, of f of x, for the most part, I'm not saying this is always true, but for the most part in this intro section, if you can plug in the value, if the expression you're looking at is defined at the value that x is approaching, more often than not, you can get the limiting value by just plugging the number into the expression and simplifying. I'll just say that I'm not really going to write that because again, technically that's not what you're doing when you're evaluating a limit. You're not plugging the number in. You're supposed to be plugging in values near that number. But a lot of times the limiting value will just end up being what you would have gotten if you plug the number in itself. Okay. So this first question, use the limit laws to evaluate. We have the limit as x approaches -1 of the following, rational expression. You got polynomial divided by polynomial. And we're asked to submit an exact answer. So that's just to get you from not plugging in, a giant decimal answer with like 8 or 9 decimal places. They want an exact answer here, so not an approximate one. So I'll go through, let's write this out. So we got the limit as x approaches, -1. And this is a two-sided limit, right? There's no little plus or minus above here. So approaching -1 from the left, and then also from the right. Hopefully they're the same. And then the expression is -3x cubed minus x minus 4 divided by, and then the denominator is another polynomial, 3 minus 3x cubed. Okay. So one of the laws that you will come across in the reading or in the further instruction, you got a quotient law. So that is if the limit as x approaches a of f of x, say that limit exists and is L, right? So some expression when x gets nearer and nearer to the a value, f of x gets closer and closer to having a value of L. And the limit as x approaches a of, say, g of x, right? Some other expression. Say this limit is another value called m, where m is not 0. Okay, so again, as x approaches a, you plug in values closer and closer to an input of a. This output, g of x, gets closer and closer to this value of m. But m also is not 0 here. Then, if you were to take the limit as x approaches a of the ratio of these two, divide them, take f of x divided by g of x. As long as the denominator is not approaching 0, right? So this, again, as x approaches a, this denominator expression is approaching some value that's not 0, well, then you can just say it's the limit as x approaches a of the numerator, split it up. Do the limit of the numerator divided by the limit as x approaches a of the denominator, and get, L divided by m, whatever this value is. So that's one of the laws that I'll be applying here. Now, of course, go through a couple more that I will apply in this particular question. Another one I'm going to be using is the sum, SUM, the sum or difference law. So I'm going to start off with this same deal. So again, if you have two expressions whose limits you know, whose limits exist, so limit as x approaches a of f, so have that be the beginning of this sum difference law. So if the limit as x approaches a of some f expression is L, and the limit as x approaches a of some g function, g expression is m, where this time m could be 0. Right? The only reason m couldn't be 0 in this one was because it was in the denominator. But when we're doing sums and differences, it can be 0. Then the limit as x approaches a of, and then say I were to add or subtract them, so f of x, plus or minus, 1 with the plus or with the minus g of x, you can go term by term and say this is equal to the limit, again, as long as these limits exist, right? Limit as x approaches a of the first term, which is f, and then plus or minus, and then the limit as x approaches a of the next term, which is g, and these both exist, and one's L, one's M. So we get L plus M in the sum case, L minus M in the difference case. Another law that's going to come up in my evaluation of this limit using the laws is the constant multiple law. So again, if the limit as x approaches a of some expression called f exists and is L, and say c is just some number, a constant, then the limit as x approaches a of some constant multiple of our original function. And so I take our original expression, multiply it by some number, some constant c. So this would be like the coefficient of f, c for coefficient 2 or constant. You can just kind of pull that out, pull c out, and have it be c times the limit as x approaches a of just the original expression f, and that exists and is L, so we end up with, c times L. All right, so coefficients, constant multiples can kind of be pulled out of limits. Another one that I'll be using up here is a constant, just the plain old constant law. So this is just simply the limit as x approaches a of a constant. So again, I'll just have c be a constant down here. Is just the constant itself. I hope that's obvious, right? This expression is always the value of c, no matter what x is. So clearly as x approaches a, you still have a value of c. The limit is c. And then there's another law that'll be applied. Most of the laws will be applied here. You got the identity law. Again, hopefully this is obvious. The limit as x approaches a of just the, if the expression was just x, if x approaches a, then x approaches a. All right, so again, hopefully that's obvious. And there's a power law that'll be applied here. The limit as x approaches a of, say, x to the nth power. And so n is some power here that's x to the n, is just a to the nth power. Right? As long as now n can't be a negative number, and a can't, if n were negative, you can't have x approach 0 here. Again, as long as you're not dividing by 0 or doing anything that's undefined. And actually, to extend this, you got the product law. So limit as x approaches a of, say, f times g would be the limit as x approaches a. So I know I said I wasn't going to write them all, but it looks like I'm writing most of them. Times the limit as x approaches a of g. And as long as both of these exist, this was L times this was M earlier, right? As long as these exist, it's just equal to their product. The limit of the product is the product of the limits. And then to kind of extend this to our power here, take the limit as x approaches a of some expression, to a power. That's just going to be L to the nth. If f is approaching L, then this kind of just have f. This will approach L to the nth power. All right, so a lot of limit laws here. Again, that's not in the works for roots. Roots are powers and everything, composite functions. Lots of stuff. All right, so back to here. I'll explain what they're asking you to do, and then just kind of, again, say what I said at the beginning of the video, or the beginning of this part. You'll see after I'm done with this that basically we get what we would have gotten if we just plugged -1 in. So look, I got a fraction here. So first of all, I'm going to see if the denominator limit even exists. So let's look at the limit as x approaches -1 of the denominator, 3 minus 3x cubed. And then I apply the sum. I'll just write the name of the laws I'm using. The sum law, sum or difference law, I'll just put sum diff. Say, hey, this is an adding or subtracting here, so I go term by term. This should be the limit as x approaches -1 of just, the first term, which is 3, minus, and then the limit as x approaches -1 of the second part, the 3x cubed. And then here I'm using the constant law, right? That's just a constant, 3. Here I can pull out this coefficient of 3. That was that constant multiple law. Now the limit as x approaches anything of just 3 would be 3, right? So value of 3 there. And then I minus, and then I pull this 3 outside the limit 3 times. The limit as x approaches -1 of just x cubed. And then apply the power law here, that power law I mentioned here. You got 3 minus 3 times, and then the limit as x approaches -1 of just x cubed, and then apply the identity law I reviewed earlier, right? So this is a little annoying, but a little tedious. So we get 3 times, and then -1, right? As x approaches -1, x will approach -1 to the third power. But do you see how this expression at the end here is just the original expression, the original polynomial, where -1 is plugged in? And when I simplify this, this would be 6, right? Because -1 cubed is -1 times -3 would be +3, and that's not 0, right? So I can apply that quotient law, right? Since the limit of the denominator exists and is not 0, I can apply the quotient law, say this is equal to the limit as x approaches -1 of our numerator polynomial divided by the limit as x approaches -1 of our denominator expression. And again, I told you earlier, for your polynomials and most of the time, a lot of these expressions, as long as things exist and whatnot, you'll just be able to plug them in and get the limit. So I already got, the denominator was approaching 6, just plugging -1 in. And if I were to plug -1 in, I would have to write out the difference law, go term by term, and pull out the -3 with the constant multiple law, and have x approach -1 with the identity law, and it would end up being just the same value that I get if I just plug -1 in right now. So -1 cubed is -1 times -3 is +3. So that's 3 minus -1 is +1 is 4. And then -4 is 0. Okay, so this limit up here, right? Again, it's +3, +1 is 4, -4 is 0. So the numerator is approaching 0, right? The limit is 0, and the denominator is approaching 6, and then 0 divided by 6 is simply 0. So this is what I'm entering for the limit. Now, if you go back to what we did in previous assignments, the limit of a function, we can try to doubly or even triply verify this. Take this expression, graph the function, look at a table, and see what happens as we get closer and closer to -1. So I'll do that for this first one, maybe a couple more after. So let's go to, here's, that Desmos website, right, desmos.com. I will enter, the expression as a function here, y equals, and we had in the numerator, make sure you put your numerator in parentheses, so it's separate. It's all up there. So I had -3x cubed minus x minus 4 in the numerator, and then denominator 3 minus 3x cubed. And you see from, graphically speaking, right, here's we said as x approached -1, y approached 0. So I'll label that point, and you can see from the graph that is occurring, right? We talked about the graphical way to approach a limit in the previous section. See how when I look at the graph from the left side of -1, you're approaching this point, this location with an output of 0. And then from the right side of -1, you're also approaching that same location, right? -1, 0. So the two-sided limit at -1, they would say, is 0. You could have also seen this from a table, right? Go to settings, make a table for this. See what happens when I plug in values, closer and closer to -1. Now, say from the left, that'd be -1.1, -1.01, 0.001, 0.001. And you see how the outputs are getting really, really small. See, that's 1.6 times 10 to the -4th means move the decimal place to the left 4 places. So that'd be 0.0001. So you see how from the left side, approaching 0, and from the right side, plug in values greater than -1, so -0.9, -0.99, 999, 9999. And again, you're seeing the output getting very, very tiny. So you can see it from the graph, approaching this point, -1, 0 on both sides. You can see it from a table. But like I said, most of the time, though, through this limit laws section, you're pretty much, again, not all the time, but in a lot of these, you'll be able to just get the limit by plugging the number in. The law is basically boiled down to plugging the number in if you can. All right, if the denominator was approaching 0, then I couldn't apply this limit law, right? I couldn't plug in the number because you can't divide by 0. And we'll get to some problems like that, I'm sure. All right, so for this first one, the limit is 0. So I'm typing in just the number 0 here, submit, and if you're correct, it'll give you some green banner with some encouraging words. If you're incorrect, it might have you try again with the fill in the blank, but you'll see a red banner still with encouraging words, keep trying or something like that. Then after you're done with the question, you'll see some sort of answer explanation. I would suggest reading through these, whether you're correct or incorrect. If you're right, read through them and see if you see it, if they do something in a better way than you did, a faster way. Maybe you want to try that for a problem in the future on the same objective, same kind of problem. And of course, if you're wrong, read through the answer explanations and try to figure out where you went wrong, and hopefully fix it for future problems like this. So yeah, hopefully you can see that, see how they're applying all these limit laws one little step at a time, eventually to get down to what I said earlier about just plugging it in, get 0 divided by 6 is 0. All right, so moving on. So again, I should be getting this objective multiple times in a row because it's the only objective in this section I'm in here. All right, so here it is again, use the limit laws to evaluate the limit of a function. So yeah, this, again, I'll write this one out, again, one little step at a time, right? You're applying the laws. So I got these, I'm given these two limits, that exist and are some finite value. We're told that the limit as x approaches -6 of f is 6, and the limit as x approaches -6 of g is -8. And we're asked to evaluate this, right? So I'll write this out. So again, we're told this, right? Limit as x approaches -6 of this f function is +6, and we're also told that the limit as x approaches -6 of this g expression, whatever that is -8. So the limit as x approaches -6 of, the expression they give us, you have -3 times f, and then plus and 6 times g. And I see a sum here. I see some constant multiples. So I can go term by term and also pull those constant multiples out. So eventually, after applying all the laws, you'd have -3 times the limit as x approaches -6 of the f function, plus, and then again, go do the next limit, next term, pull the 6 out, right? Constant multiple law. 6 times the limit as x approaches -6 of the g expression. And each of these was given to me, right? So this is end up being -3 times, this limit as x approaches -6 of f was +6, plus, and then 6 times, and this limit as x approaches -6 of g was -8. And we'll simplify this numerical expression here, right? -18, -3 times 6, plus, -48. So -48 there, and this will be -66 when you put it all together, and that's got to be the limit in question. So that's what I'm entering. Going back here, and just says provide your answer below, -66, and submit. And again, they once again state all these limit laws and how they're applying this particular problem one step at a time. But hopefully it's, again, it's just it ends up being a simple substitution at the end. All right, once again. So again, as long as now there's a root law as well. Just, remember you can't take square roots of negatives. So as long as you're not ever plugging in numbers that will make you take the square root of a negative, you should be able to just do a direct substitution. So you got this polynomial, 9 minus 7x multiplied by this radical, square root of 6 minus 4x, and we're taking the limit as x approaches -3. Right, so if you see that -3, can be plugged in here, values around -3 as well, close to -3 on either side can be plugged in, and you have 6 minus, 4 times -3 is -12. The times negative, then you got the opposite of that though. So this would be 6 plus 12. This would be the square root of 18, which is fine, right? You're not taking the square roots of negatives. The only time I'd worry is if this was the square root of 0. That means, one side it might be negative, the other side positive. So, but this is going to be the square root of 18. And then outside the square root, negative 7 times negative 3 is 21, plus 9 is 30. And you can seriously just enter, 30 times the square root. I put the symbol in. All right, so there's the symbol of 18. Now I know that the square root of 18 simplifies. The square root of 18 is the square root of 9 times the square root of 2, which is 3 root 2. So this would be 30 times 3 root 2, or 90 root 2. So you're going to see that answer show up. But if it just says submitted exact answer and there's nothing telling you to simplify completely, you don't have to put in a simplified answer. As long as what you put in is equivalent to the simplified answer, it should be taken in, right? So again, if I just substitute negative 3 here and simplify a little bit, we got 30 times the square root of 18, and that should be good. So again, see how they have 90 times the square root of 2? It's only because they actually simplified the square root of 18 to, be 3 times the square root of 2 and then multiply by 30. Once again, all the laws listed that were used here. So notice how in the root law for limits, as long as, when you're taking an even root, right, as long as that limit is non-negative, you're fine. Right? You can just kind of plug things in. Remember, an odd root, you can have any number inside an odd root, so see how it's for all L and all that. All right. All right, so another one here. So this is very similar to earlier, where I'm just making a substitution, really. As long as, I got a fraction here, as long as the denominator is not going to 0, I can just make simple substitutions. So we're told that as x approaches negative 8, this f function is approaching negative 3, has a limit of negative 3. And then as x approaches negative 8, the g expression is approaching positive 3. We're asked to do this. What's the limit as x approaches negative 8 of f squared in the numerator divided by, and then g cubed in the denominator. Well, f should be going to negative 3, but negative 3 squared is 9. So I have 9 in the numerator divided by, and then g is going to 3. So this denominator should be going to 3 cubed. 3 cubed is 27. Like I said, they said submit an exact answer. It's nowhere in the instructions do I have to simplify. Now 9 divided by 27 is 1/3, but this should be acceptable. And you see it is correct, and I've now completed the one of those 8 objectives. So you see they simplified to 1/3, but again, if they don't specifically say simplify, just enter an exact answer, you can enter something that is equivalent to their simplified answer, and it should work. All right, so now we're moved into this evaluate a basic limit. All right, so all those limit laws I mentioned earlier work for not only two-sided, but one-sided, right? So if you're approaching a value from the left or from the right, but the expression you're looking at, you can just plug the number in and not divide by 0 or take square roots of negatives, even roots of negatives, or logs of negatives, or something like that. You can pretty much just substitute. So yeah, so we're going to be in these two objectives for a bit. So use one-sided limits to evaluate a limit using limit laws. Right, so find the two one-sided limits as x approaches negative 3 of, this is called the floor function. And so we want the limit as x approaches negative 3 from the left, limit as x approaches negative 3 from the right. Now the floor function, see this little thing with the around x, the output is simply the largest integer that's less than or equal to the input. So I'll show you the graph of this thing in Desmo. So I'm pretty sure you can just type in floor, y equals floor of x. So again, see the output. So everything between 0 and 1 would map to 0. And then at 1, so there's a 1, 0 shouldn't be there. 1, 1 is the next point. That should be an empty point, 1, 0. Then 1 would map to 1, and everything between 1 and 2 would map to 1, have an output of 1, and then everything between 2 and 3 would have an output of 2, and so on. Now we're asked around -3, right? So here's -3, and you see how everything, when you're to the left of -3, you're approaching this point with an output of -4. When you're to the right of -3, you're approaching this point with an output of -3. So the left side limit is -4. The right side limit is -3. So that's what I'm entering here. So left side limit, -4. So again, you'd be on this piece, right? You're the piece where your x is between, -4, -3, right? We're on the left side of -3. So the output's -4 on the left side of -3. And then on the right side of -3, I'd be on this piece here where x is between, -3 and -2. And in that case, the output is -3, right? So left side -4, right side -3, and submit. Right, it's really, really simple, that one. And they show you a picture here. See how they should be open points at the right ends. Great. All right, so here's one where you got to really pay attention. So again, I mentioned earlier that a lot of times you'll be able to just plug the number in. Sometimes, if things are undefined, not part of, if your inputs are not part of the domain of the expression, you can't just plug in the number. So I'll write this up here. Okay, so here we have the limit. As the first one is the limit as x approaches -2, from the left, you got the little minus sign there, of the square root of -4x minus 8 plus 3. Oh, sorry, plus 3 is not in the square root. So it's the square root of -4x minus 8 and then plus 3 after, okay? So here's what I meant by you can't always just plug it in. Because if I were to plug it in, right, if you just plugged in, x equals -2, then you'd have the square root of, -4 times -2 and then minus 8 and then plus 3. And this is 8 minus 8. This is just 0, and 0 plus 3 is 3. So you might say, oh, the limit is 3. But pay attention. Right? Let's remember, when you're taking limits, you're not supposed to actually be plugging the value in. This is always about what happens as we approach the value. So when x is approaching -2 from the left, that means x is a value less than -2. But these numbers are, if I plugged in, say, -2.1, -2.01, the big question is, are these values allowed? Are they in the domain of the expression? All right. So, because if they are, then this is fine. Okay, we'll be approaching 3. But if they're not in the domain, then I can't even think about plugging them in, and the limit, doesn't exist. So here's the expression, right? You got the square root of negative 4x minus 8, and then plus 3. So remember the expression inside a root, if it's even, right, this is square root, has to be non-negative, right? So negative 4x minus 8 in here has to be greater than or equal to 0. Now if I were to add 8 to both sides, that means negative 4x must be greater than or equal to 8. And then dividing by negative 4 would flip the symbol, right? Dividing by a negative. 8 divided by negative 4 is negative 2, and again, that would flip the symbol. So here's the domain, right? The domain of the expression is this. Now, are these numbers less than negative 2 in the domain? Yes, right? So the answer is yes for these. So this is fine. I can apply all those limit laws, which basically boil down to kind of just substituting. So this limit as x approaches negative 2 from the left of this expression is, positive 3. And I'll go to a graphs and we'll see that as well. We'll approach a point with a y value of 3 to the left side of negative 2. Now look at the other one. Yeah, so the limit as x approaches negative 2, from the right of this, same expression. But this time, when we're approaching negative 2, from the right, that means the values we're looking at are values greater than negative 2. So negative 1.9, negative 1.99. These are not in the domain of this expression, right? The only values I'm allowed to plug into this expression are values less than or equal to negative 2. Values being discussed here with this notation are greater than negative 2. They are not less than or equal to negative 2. So this limit simply does not exist. There's nothing to do, all right? There's no graph to the right of negative 2, and I'll show you that. Go to Desmos. So here's the expression we were given. I'll make it a function. Y equals, the square root. And then you have negative 4x minus 8 inside the square root, and then plus 3. And then here's the point. We said the left side limit was 3. So here's the point, negative 2 comma 3. Right, and I'll label that. And you can see that to the left side of negative 2, the graph is definitely approaching that location. Right, to the left side of negative 2, the graph is approaching this location with a y value of 3. So the left side limit is 3. But you see how to the right side of negative 2, there's nothing. There is no graph over here because these values to the right of negative 2 aren't in the domain of the expression. So I can't talk about, some limit as x approaches negative 2 from the right because there are no points where x is to the right of negative 2. So that limit, the right side limit, does not exist, right? So again, the left side limit, 3, and the right side limit, right, if the limit does not exist, you're entering this circle with the slash symbol, the empty set symbol, for your answer. Again, they show you the graph here, right? All right, so we're switching objectives. Again, it's just these two for now. It's going to go back and forth between these two in this evaluate a basic limit part of the section. So find the limit of a polynomial or rational function using limit laws and direct substitution. All right, so this whole direct substitution is what I've been mentioning. Basically, if the value you're plugging in or values around what you're plugging in, because again, when I say the limit as x approaches negative 3, that means you're supposed to be plugging in values close to negative 3, but not negative 3 itself. But as long as those values and the value itself belong to the domain of the expression, you pretty much can just do a substitution. Also, you don't want to have, division by, again, as long as it belongs to the domain. So you can't be dividing by 0, can't take even roots of negative numbers, logarithms of non-positive numbers, right? let's see, there's some, things with trig functions involved, right? Again, as long as your value is in the domain of the expression, you can pretty much most of the time just do a direct substitution. So like here, so again, I'll write this first one out for this objective. So we got the limit as x approaches -3 of some rational expression, right? Polynomial x cubed plus 5 in the numerator divided by polynomial 2 minus 3x in the denominator. So yeah, as long as the denominator isn't 0 when I plug it in, I can just do a direct substitution. The limit exists, so like I'll just do 2 minus 3 times -3. So again, technically x does not equal -3, but we're gonna, if the denominator is not 0, or again, as long as x equals 3 is in the domain, x equals -3 is in the domain of this expression, then we can just try direct substitution. So I said it doesn't always work, right? Sometimes your function might be a piecewise defined function, so it's different from one side than it is from the other, or a radical like the last example with the square root and all that, so like it doesn't always work, but a lot of the times here, especially with like polynomials and rationals and a lot of the functions classes you came across in pre-calculus, for a lot of those, you'll just be able to do a direct substitution. Numerator, same thing, -3 cubed plus 5, just kind of plugging it in, and then we'll simplify. Now it does say, again, it just says enter an exact answer. So I'll just say what the numerator is. That's -27 plus 5, so I got -22 in the numerator. And then 9, plus 2, 2 plus 9, 11 in the denominator. So you could enter this. This should be fine. But that's a pretty easy one to simplify. This is -2. All right, so the limit is -2. Once again, if you wanted to make a graph, I'm not going to make a whole graph here, but if you wanted to go graph this in Desmos, as x approached -3, you should be approaching a point with a y value of -2, right? You should be approaching this location on both sides, right? The graph should be going to that location on both sides. And and it actually would be filled in too, because, -3 is part of the domain. There'd be a solid point there. So you can go look at a graph, look at a table if you wish. Like I said, a lot of these, if you can plug it in, just plug it in. All right, should be working out. So yeah, the limit here is -2. And again, they go through and mention how, as long as denominators aren't 0, just plug stuff in. Same thing for polynomials, you just plug stuff in for these limits. So this is really no different. Polynomials, the domain is all real numbers. These are defined everywhere. And so when I'm doing a limit, you can just simplify it real easily, just do a direct substitution. So I'll just save this one as x approaches -1, 4x cubed minus 3x squared plus 5. Do your powers first, right? -1 cubed is -1, -1 squared is +1. Then your multiplication, 4 times -1 is -4, -3 times 1 is -3, and then your addition or subtraction, right? -4 plus -3 is -7, plus 5 is -2. So this should have a limit of -2. Great. Now they're not all -2. All right, just be aware of that. You might get some other numbers, some other problems, right? All right. So again, back to the paying attention to, I mentioned earlier, piecewise defined functions. You really got to pay attention to what side of a certain value you are on to know what piece you're plugging into. So here, for the function, this piecewise defined function here, evaluate what happens to the value of this function as x approaches -3 from the left, from the right, and then two-sided if it exists. Right? So so again, I'll write this one out. So again, you can do some plugging in, some direct substitution, but you got to pay attention. Know what piece you're on, what expression you're working with, right? So here's f once again. So f of x is, now the way the output is negative, the opposite of x squared minus 2x, but that's the output if the input is smaller than -3. And you just get the opposite of x if the input is greater than or equal to -3. So the limit as x approaches, -3 from the left of this function. So again, pay attention, right? From the left means the value of x is smaller than -3. So that's, I'm up here. So I'm going to rewrite this as the limit, as x approaches -3 from the left, the expression I'd be plugging my values into is this one here, -x squared minus 2x. And since this is a nice polynomial defined everywhere, I can just do a direct substitution and just kind of plug in -3. This will be the opposite of -3 squared minus 2 times -3. And simplify, right? So this will be the opposite of 9 and then plus 6. So -3. And so my left side limit is -3, and meaning on a graph, we'd be approaching this point here, -3 comma -3, but only on the left side. All right, so something like that, right? But it would be an empty point, right? On this first piece, x is not equal to -3, just less, right? So I'm approaching that location. It doesn't have to be there. And then the right side limit, and this -3 from the right means x is greater than -3. So I'm definitely on this second piece, plugging into this second expression. And again, we have this negative x, and we have a polynomial. So I'm just going to do a direct substitution. This is the opposite of -3, which is +3. All right, so you can go to the graph, and now this would be solid because you got the or equal to -3 up here. So here's the point, -3, +3, and the graph would be approaching, that location from the right. So you see from the left side, it'd be approaching this -3 value. From the right side, it'd be approaching this +3 value. Right, so then the two-sided limit doesn't exist because they're not approaching the same location on both sides, right? So from the left, -3, from the right, +3, and then again, does not exist for the two-sided, so I'm putting that empty set symbol. And again, here's a picture of the graph. I had this coming in from the wrong direction. I just made a rough sketch, right? But just, and see approaching the point -3, -3 on the left side, approaching the point -3, +3 on the right side, right? So no non-existent two-sided limit. Absolute value. Okay. So it's like a polynomial thing, right? As long as you're not dividing by 0, you can do a direct substitution. So as I approach 2 from the left or from the right, this will approach the absolute value of 6. 3 times 2 minus 9. 6 minus 9 is -3, but the absolute value of that is +3. And it doesn't matter from the left, from the right. That's not changing. So both of those are 3. You could even look at the graph, right? Now, absolute value, you can just type in ABS, y equals, the absolute value of 3x minus 9. And I said the limit was, 3. So there's the 0.23. I labeled it. So you can see that on the left side of 2, approaching that location. On the right side of 2, approaching that location with a y value of 3. So the limit is 3 on both sides. Wonderful. All right, so that objective's done. So another one where you're just doing substitution. As long as the denominator is not 0, you're fine. So I'm just going to say this one out loud. Again, if you want to write it out, fine, but I've already done one of these where I wrote it out. Unless it gets too complicated, then I'll write it out. But, -1, x is approaching -1. And again, these are polynomial over polynomial. When x approaches -1, the denominator would not be approaching 0. It would be approaching, 4 times -1, which is -4 minus 2. That's -6. So -6 denominator, and, -1 cubed is -1. -1 squared is +1. So you have 5 plus 5, plus 2. You got 12 in the numerator, -6 in the denominator. So again, -2, right? And not always -2. Please know that. So yeah, this would be approaching -2 as x approached -1. Another one like this, again, denominator will be approaching the opposite of -3, which is 3 minus 1 is 2. So the denominator is approaching 2. Now -3 squared is 9. So you got -9 minus -3. So -9 plus 3 is -6. And -6 plus 4 is -2. You have -2 in the numerator, 2 in the denominator. So -1 would be the limit. If you simplify it again, you can enter it as -2 or 2 over -1. Sorry, we got -9 plus 3 is -6 plus 4. Yeah, so -2 in the numerator, and then +2 in the denominator. So if you put -2 over 2, it should take it, but it's -1 when simplified. Okay, so a lot of direct substitution there. So now we're getting into this group where you have additional limit evaluation techniques. So this is where you're going to not be able to just plug the number in immediately, because you'll have a denominator of 0 or something like that, something that makes the expression undefined. So if that's the case, then you got to manipulate the expression or think about it in some other way, write an equivalent expression that you can plug into. So watch, right? So you got the limit as x approaches 1 of this 1 over x minus 1 plus 6 over x minus 1 times x minus 7. Now, I cannot just plug 1 in, right? Because you'd have divided by 0 there, divided by 0 there. You'd have denominators of 0. So don't just say this is undefined immediately, all right? If that's the case, you can't just plug the number in. You can't just do a direct substitution. Manipulate the expression. You're going to have to use some algebra to manipulate the expression to an equivalent expression at values, around x equals 1, right? So here we got the limit as x approaches 1 of this 1 over, x minus 1. And I'm going to put this in parentheses, this denominator here. Then plus 6 over x minus 1 times x minus 7. So again, I can't just, this means that x is approaching 1 from both sides. X is not 1. So again, I can't just plug in 1 here. That wouldn't work. You'd have divided by 0, divided by 0. So I want to rewrite this, get these together, rewrite this out, use algebra, some techniques from algebra to rewrite this in a way where I could just plug in 1, instead of going to a table or a graph. Now you could go to a table, go to a graph and try to figure things out. But if the number's not a nice whole number, you're probably not going to be able to tell what the limit is exactly, and they want us to submit an exact answer here. So I want to eventually get rid of the problem. The problem here is this x minus 1 in these denominators, right? That causes the problem. That makes me divide by 0 when I just plug it in. So I get these together. Now, remember when you add or subtract anything, you need a common denominator. So they both have a factor of x minus 1. So this one's just missing the x minus 7. So I'm going to multiply the numerator and denominator of this fraction here by x minus 7. So now I have a common denominator, right? This x minus 1 times x minus 7. So that'll be the denominator of their sum. And then, the numerators are 1 times x minus 7. That would just be x minus 7. And then plus 6. But x minus 7 plus 6 is just x minus 1. So I have x minus 1 in the numerator, and then x minus 1 times x minus 7 in the denominator. And then as long as x is not 1, these will be the same. This x minus 1 and this x minus 1 will be the same non-zero number. And when you divide two numbers that aren't 0, you get 1. So this limit is equivalent to the limit as x approaches 1 of 1 over x minus 7. So you see what I've done is I got an expression. This 1 over x minus 7, this expression has the same value as the big one from the beginning, except at 1. Because at 1, this expression in the beginning is undefined. But down here at 1, it's negative 1/6, right? Now I have something that I can do a direct sub. I can sub x equals 1 in. Again, technically you're doing values around 1, but now I can apply those limit laws, which eventually boil down to direct substitution. So this limit is 1 over 1 minus 7, or negative 1/6. So that's it. And again, you could make a graph of this, go to a table, have the value of x get closer and closer to 1 on both sides, and you might have seen that the value approaches, negative 0.1666, forever. That's what negative 1/6 is, but, it's just easier to go about it this way algebraically. So enter negative 1/6. And again, please read through the answer explanations. Right. Yeah, so here's one of those where, again, you can't just substitute the value, right? You can't apply those limit laws here. Because if x is 0, now we're having x approach 0, remember? But if I were to plug in x equals 0, you'd have a denominator of 0. Also, the numerator would be 0, and that 0 divided by 0 is something we'll come across a lot later too. So like that out. So we got the limit as x approaches 0 of, and then your expression is 4 minus, and then up here you got 3x plus 2 squared, and then divided by 9x. So if we just plugged in x equals 0, and I know that technically, right, what this really means is x is not 0, you're just approaching 0. But if I were to plug this in, you'd get 0 in the numerator, 0 in the denominator. And this is meaningless. This 0 divided by 0 has no meaning whatsoever. Don't say this is 1. The only time you divide something by itself and get 1 is if they're not 0, like 5 divided by 5 or 7 divided by 7. 0 divided by 0, they're going to call this an indeterminate form. And this is just one of 7 that we'll come across in this course. But when they say it's an indeterminate form, means you can't determine the value. It has no meaning. You can't say what this value is right now. So we gotta manipulate the expression again. So I'm going to use algebra here, and I'm going to manipulate it in a way to where I can use the limit laws, right? I can't use the limit laws here because the denominator is approaching 0. Now the numerator is a difference of squares, right? Because that's 2 squared minus 3x plus 2 squared, so I should be able to factor it. Remember, you can factor a difference of squares to a minus b times a plus b, so that'd be 2 minus 3x plus 2 in one of the factors. times, and then 2 plus 3x plus 2 in the other factor. And then here, when I'm subtracting 3x plus 2, I'll distribute that. And I have 2 minus 3x minus 2. That's just negative 3x. Right? So I got negative 3x in the one. And then here, this is just the 3x plus 4 divided by, 9x. And now you can see the x's canceling, right? Because again, x is not 0. X is approaching 0. I got a factor of x divided by another factor of x, right? And those will become 1. And 3 goes into 9 3 times as well, so I'll simplify that. So this limit I started with is the same as this limit. The limit as x approaches 0 of, negative quantity 3x plus 4 divided by 3. Again, because 3 goes into 9 3 times. The x is canceled. Yeah, so again, this expression I just wrote, this has the same value as this initial one everywhere except at 0. Right? When you plug 0 in up here, you get 0 divided by 0, which is bad, meaningless. But if I plug in 0 down here, I actually get a value. This would be negative 4/3. When x is 0, this is just before, and then you got over 3. So negative 4/3 is our limit. So and you could have done this without all this. You could have gone to a graph, gone to a table, and maybe figured it out by looking at it. But if you were to enter this expression and have x go closer and closer to 0, and then look at a table, you would see the outputs get closer and closer to negative 1.33333, That's negative 1 1/3, negative 4/3. Again, I think this is easier, but you might have been able to tell that from a table or a graph as well. Right, so this limit, negative 4/3. All right, so this one has some complex fractions. So again, it's one where if I were to plug in the number, so x is approaching negative 10 here. If I were to plug in negative 10, you get 0 in the numerator, 0 in the denominator, which is bad, right? All right, so here's one where I'm simplifying a complex fraction. So we got the limit as x approaches, negative 10. It's 1 over negative 9x minus 3 in the numerator, minus 1/87th also up there. And then big bar, divided by another difference of fractions down here, 1 over negative 9x minus 9, and then minus 1/81st. So again, if I were to plug in, do the bad thing, x equals negative 10, and technically x is not negative 10. But if I were to do a direct substitution, say I can apply the limit laws, you'd end up with 0 in the numerator and 0 in the denominator again, right? So this is bad. You can't say anything. 0 divided by 0 is one of those indeterminate forms, meaningless. So I have to then simplify this. All right. Now, I'll work with the numerator expression and the denominator expression separately. So when I'm putting this numerator together, now I'll just factor the denominator. I want to factor my denominator, so I'm trying to get a common denominator, right? So I'm going to pull out negative 3 from that. And if you pull out negative 3 from negative 9x minus 3, that'd be negative 3 times, 3x plus 1. All right, that's negative 9x minus 3. And then minus, 1 over, and then 87 is a multiple of 3. So that's, 87 is 3 times 29. All right, so if I'm just working with the expression above the bar here. And so I need a common denominator. All right, so I'm going to multiply this fraction by, it's just missing a 29. All right, it's got a factor of 3. And in fact, I'll put this minus up here. I multiply that by my negative, so make this -1 over 3 times 3x plus 1. There, now they both have this factor of positive 3, and this is missing 29, so I need to multiply this by 29 over 29, and this fraction is missing the factor of 3x plus 1. Okay, and then putting these together, we get the following, right? They both have this common denominator of 3 times 29 times 3x plus 1. And then putting the numerators together, you got this numerator is -29 minus, and then this numerator is, the quantity 3x plus 1, and I'll distribute the negative here, and we get, so this is going to be above the main bar. All right, so you got -3x, and then here's -29, minus 1, be minus 30 over 3 times 29 times 3x plus 1. And I'll simplify this a little further. You can divide each of these by 3. I could factor 3 out of here. Actually, I'll factor a -3 out. And, -3 times x plus 10. That's -3x minus 30 divided by, and then 3 times 29 times 3x plus 1. And 3's cancel. So this is just the numerator. You got -1 times the quantity x plus 10 divided by 29 times the quantity 3x plus 1. Right, so that's just the numerator put together. I'm going to do the same thing with the denominator, everything below the main bar. And this is -1 over 9 times x minus 1. All right, again, I factored out -9, put the negative up top, so that's 9 times x plus 1, sorry. If I factor out -9, this would be -9 times x plus 1, and then put the negative up top. That's what give me this down here. And then minus 1 over, and then 81 is 9 times 9, just to have the, see that they both have factors of 9. And so this is missing a 9, it needs another 9, so I multiply this by 9 over 9. This one's missing the x plus 1 factor. Now I have a common denominator. So this 9 times 9 times x plus 1. And the numerators are -9 minus this x plus 1. Distribute the negative. So again, this is all separate. So it'd be -x minus 10 divided by, and then down here, 81 times x plus 1, 9 times 9 times x plus 1. And if I factor out a negative from the top, that's -1 times x plus 10 divided by, and then 81 times x plus 1. Okay. So we've got this expression is in the numerator. This expression is in the denominator. So when I divide these, it'll be the top expression. So the opposite of the quantity x plus 10 divided by 29 times 3x plus 1. But then when you divide by something, you multiply by its reciprocal. So I'm going to turn this into times the reciprocal of this, which is 81 times x plus 1 now in the numerator, and then this negative, x plus 10 in the denominator. And then you can hopefully see some stuff canceling. Both of these have this negative factor, an x plus 10 and x plus 10 factor. All right, so after all that, and I don't think 29 goes into 81 evenly. They don't have any common factors. So we get the limit as x approaches, -10 of the following expression. 81, I've got 81 times x plus 1 in the numerator, and 29 times 3x plus 1 in the denominator. And here's, so this, I know it's tiny, but this expression here has the same value as the original one everywhere except at -10, right? In the initial one, I couldn't plug -10 in, but now I have something. See, these x plus 10s canceling really help. Now I can plug in -10. So you get 81 times, -9 in the numerator, right? -10 plus 1 divided by, and then 29 times -30 plus 1. So -29 in the denominator, and I'll just, type these values in somewhere. It's yeah, you got, well, this is 729, right? 81 times 9 is 729. So it's negative, so it's 729 in the numerator, and just 29 squared. 29 times 29 in the denominator. So 729 over 841, right? And it would be positive, right? Because again, these are both negative, so it would be positive 729 divided by 841. Now that's definitely something you couldn't tell me using a table. This would be some crazy decimal. So I go back to here, that's what I'm entering, right? It says enter an exact answer. So 729 in the numerator, divided by 841 in the denominator. Okay. Oops, sorry. Back to the website. So yeah, definitely something, 729 over 841. So again, definitely something you probably couldn't tell me just from looking at values on a table or looking at a graph even. Right, so again, simplifying complex fractions, they did all the stuff I did there, just on the same lines. Read through them carefully. All right, so another one where and I can't just plug in 0, because once again I'd have 0 in the numerator, 0 in the denominator, one of these indeterminate forms, one of these meaningless forms. So I must either use a graph or a table and be really good at figuring out the value, or manipulate the expression algebraically. Okay, so -2x. So again, I can't just plug in 0. Right, and x is not 0 here. We're approaching 0. But if I were to just do a direct substitution, you'd have 0 in the numerator, 0 in the denominator. Right? So that's bad. So when they have these expressions with roots and you want to rewrite it another way, try multiplying by the conjugate. So you got the square root of 4 minus 2x and then plus 2. And do the same to the denominator. All right, so again, these are conjugates. Remember, when you multiply conjugates, you end up with a difference of squares. So this expression here, the numerator, is now the square root of 4 minus 2x, squared. So that's just 4 minus 2x, and then minus, and then 2 squared. So 4. So that's the numerator, multiplying the conjugates. And then the denominator has this, -2 times x, and then times that conjugate, square root of 4 minus 2x, plus 2. And if I put these things in the numerator together, that's just -2x. So it's -2x in the numerator, divided by, and then you got -2x times that conjugate, square root of 4 minus 2x plus 2. These cancel, -2x, and as long as x is not 0, these will be the same non-zero number. Cancel, cancel. Got 1 in the numerator. So we end up with the limit as x approaches 0 of this expression. Now 1 in the numerator, divided by, and then that conjugate from earlier. And what I just did here was called rationalizing the numerator, right? You might remember rationalizing denominators, where you tried to rewrite an expression without a root in the denominator. Well, you can do the same with the numerator, right? It don't matter. Still the same expression. So this expression that I have down here this has the same value as this one that I started with everywhere except at 0. All right, now in this one, when I plug in 0, I get nothing. It's 0 divided by 0, meaningless. But here, when I plug in 0, I get 1 over, the square root of 4, and then plus 2, which is 1/4. All right, that'd be 2 plus 2. So the limit is 1/4, which you probably could have told from a table. Right, a table, the values would be getting closer and closer to 0.25. You might have been able to see that, right? Maybe they were like 0.2499999 or something like that. So you might have been able to get this from a table, but it's a lot easier, I feel, this way to see the exact value that the expression is approaching. So exact answer, 1/4. Right. Again, read through the answer. I'm doing all the same stuff, the rationalizing, multiplying by conjugate junk I did there. All right, so this one's just going to involve factoring. You just got polynomial divided by polynomial. And it's another one where if I just plugged in 2, even though I'm technically not supposed to, if I say, oh, I'm just going to use the limit laws and plug in the number, you'd have, 8 and then minus 8, 8 minus 12 plus 4. You have 0 in the numerator and, -8, and then minus 2 is -10 plus 10. You got 0 in the numerator, 0 in the denominator. So there's another one where you can't just use the limit laws and plug the number in. So I need to rewrite this expression in some other way where I can use the limit laws and just direct substitute. X approaching 2, 2x squared minus 6x plus 4 divided by negative 2x squared minus x plus 10. So again, this is the whole 0 divided by 0 thing, right? If you actually plugged in x equals 2, even though technically what we're supposed to be doing is plugging in values around 2, x is not 2. But it's indeterminate, right? 0 divided by 0 is not good. So I need to simplify this. Now it's a fraction with polynomials. You may recall how to simplify a fraction from, pre-calc or algebra class. And I know all this rewriting expression stuff, complex fractions, rationalizing, multiplying by conjugates, adding or subtracting fractions. And, here I'm going to be factoring and simplifying. A lot of this stuff you might not have done in a while. So you may want to do some sort of algebra refresher before you, really get into the assignment. Anyway, so up top, common factor of 2 in those, right? So it's 2 times x squared minus 3x plus 2. And then you can factor that a little further. That's 2 times, and then, again, I'm not going to go over, this is not going to be a lesson on algebra stuff. I'm just going to say what the factors are. X squared minus 3x plus 2 would factor to x minus 2 times x minus 1. So there's the numerator factored. Denominator, again, usually when the lead is negative, you pull out a negative, so it's the opposite of, and then you got 2x squared plus x minus 10. And then this, the factors of negative 20 that add up to 1 are positive 5 and negative 4. And so it's 2x plus 5 times x minus 2. Again, I'm not going to go over a lesson on factoring here. You should know how to factor, or at least it's assumed you do at this point. Brush up if you need to. And I'm seeing that these have a common factor now of x minus 2, right? And that's what's causing the problem, right? If x minus 2 is there and there, plug in 2, that gives me 0 and 0. So if I get rid of those, that will put me in a form now that's not going to be this 0 divided by 0 form. So now I have the limit as x approaches 2 of, let's do 2 over negative 1 here. Let's make that negative 2 up top. So negative 2 times x minus 1 divided by, and again, I put the negative up there, and so we just got the 2x plus 5 down here. So once again, this expression has the same value as this one, except at 2. But we're not at 2, right? We're approaching 2, so this will have the same limit that this does. But this one, though, I can apply the limit laws because the denominator is not going to 0 anymore. All right, so when x approaches 2, denominator is going to 2 times 2 plus 5, denominator is going to 9, and numerator is going to -2. Right, so the limit's -2/9 or -0.2 forever, 0.2222222, which again, you probably could have seen in a table or a graph, but if you don't know your decimals well enough, you probably might not have been able to say that the limit was -2/9. So again, just typing in -2/9 there, cool. Read through the answer explanations. Here's another one, like the previous one, where if I were to plug in 4, denominator 0, and the numerator also 0. All right, so it's another 0 divided by 0 thing. All right, so write this out, do it again. It's just more, this is polynomial over polynomial, simplifying a rational expression. So just factoring and canceling common factors once more. X approaches 4. We got -5x squared plus 21x minus 4. And then 24 minus 6x down here. So again, the numerator, I'll pull out a negative, and then you got 5x squared minus 21x plus 4, and then fact 4. And then factors of 20, that adds to -20 would be -20 and -1. So that's the opposite of 20 divided by 5 is 4x minus 4, and then 5x I said x minus 4, didn't I? It's x minus 4. Sorry, I said x minus 4, but I wrote x minus 5. It's like one of these factors is x minus 4, and then 5x minus 1 is the other one. I'm going to double check that's 5x squared minus 21x plus 4. So there's the numerator, and then from the denominator, I would pull out a -6 myself. Common factor of 6, and lead term, the highest powered term, as a negative. So I'll pull out -6, and then you got x minus 4 as the other factor. So -6 times the quantity x minus 4. And again, the whole point of doing this is to get rid of these x minus 4 factors, right? That's what's causing the issue. Because if I just replaced x with 4, those are what's making me have 0 divided by 0. And then negative divided by negative will be positive. So this ends up being equivalent to the limit as x approaches 4. Positive, and then you got 5x minus 1 in the numerator, and 6, just 6 in the denominator. And if x goes to 4, now you got 19/6 for the limit, which again, probably not something you would have been able to tell from a table or a graph. So 19 divided by 6. Cool. All right, so that objective's done. Again, a lot of those in that objective were, here's this 0 divided by 0 problem. Can you manipulate, can you rewrite the expression so that you get an equivalent, something that's equal to the original everywhere except at the value you're plugging in. And then, oh, now I can plug it in because I've simplified it in a way that works. Here's another one. This one will involve the rationalizing again, right? I got the square roots involved, right? If I plug in 1, got 0 in the denominator, and then square root of 3 minus square root of 3 is 0 in the numerator. So let's do that again. So the limit as x approaches 1, square root of 4 minus x, and then minus the square root of 3 in the numerator, and then just simply 1 minus x in the denominator. So again, huge problem here. I can't just plug in 1, but this, like one of the problems I had up earlier with the roots, I'm going to multiply the top and bottom here with a conjugate of this radical expression, which would be the square root of 4 minus x plus the square root of 3, and do the same to the denominator. Consider this together. So multiplying the top and bottom by the conjugate. Remember, multiplying two conjugates, you get a difference of squares. So the square root of 4 minus x times square root of 4 minus x, that would just be 4 minus x. And then minus square root of 3 times square root of 3 is 3. So that's the numerator. And then the denominator, I'll leave the way it is. 1 minus x times that conjugate, square root of 4 minus x, plus the square root of 3. Now 4 minus x minus 3 is just 1 minus x. So that's 1 minus x in the numerator divided by, and then 1 minus x, times that conjugate in the denominator, and the problem goes away. All right, 1 minus x, 1 minus x. Now you still have 1 in the numerator, but those were the problem. Right? I plugged in 1. Those were what caused me to have 0 divided by 0. So now we have the limit as x approaches 1 of 1 in the numerator divided by this, this conjugate thing, square root of 4 minus x plus the square root of 3. And this expression, you can check with Desmos or whatever, this expression has the same value as the original everywhere except at 1. This one you couldn't plug 1 into, however, this one you can plug into. Now this would be 1 over 2 root 3, right? Because you have the square root of 3 plus the square root of 3, so it's 2 square roots of 3. Now you don't have to rationalize. If you want to multiply the top and bottom by square root of 3, you can, and then get square root of 3 divided by 6, but I'm gonna, you can just enter it like this, because it doesn't say rationalize denominators or anything. It just says, enter an exact answer. So the way I had it was 1 divided by 2 times the square root of 3 in the denominator there. Hooray. As long as what you enter is correct and, equal to what they have, right? They have the rationalized version, square root of 3 over 6. Same value. Another one of those complex fractions, right, where I'm going to put the numerator together as a single fraction, the denominator together as a single fraction, then rewrite it as a multiplication problem, and hopefully we get rid of x plus 1s. Because again, x is approaching -1 here. If I were to just plug in -1 for x, you get 0 in the numerator, 0 in the denominator, 0 divided by 0, one of those indeterminate forms, something that has no meaning. When I'm done simplifying, I should eventually get rid of a factor of x plus 1, as a factor of x plus 1 will be 0 when x is -1. So we'll eventually see that. All right, so here was the 1 over 8 minus 3x. I'm just gonna do it here, leave some space, minus 1/11. And 8 minus 3x doesn't factor any further, 11 doesn't factor any further. And then down here, 1 over, now 6 minus 3x was the thing down here. I'm going to pull out a 3, make that 3 times 2 minus x. That's the same as 6 minus 3x. And then minus, and then 1 over 9, but I'm going to write 9 as 3 times 3, just get some factors. And so here's our original. Again, if I plugged in -1, it's bad. That's 0 divided by 0. I'm going to put things together. I'm going to put the stuff up top together. This needs to be multiplied by 11 over 11. And this needs to be multiplied by 8 minus 3x, over 8 minus 3x. So up top, you'd get this 11 times 8 minus 3x in the denominator. And then the numerators, you'd have 11, right? 1 times 11, and then minus, this quantity, 8 minus 3x. And if you distribute the negative here, that's 11 minus 8 is 3, and then plus 3x. So 3 times, it's 3x plus 3, which is 3 times the quantity x plus 1, right? This is 3x plus 3, which I factor out of 3. And I told you there'd be an x plus 1 factor eventually showing up here that we're going to eventually cancel. All right, so here's the numerator as a single fraction. Right? and then divided by, and then down here, I have to multiply this by 3 over 3 to get an extra 3, and then this by 2 minus x over 2 minus x, get a common denominator. So that common denominator is 3 times 2 minus x, and then the numerator is, the numerators put together are 3 minus, this 2 minus x quantity. Distribute the negative, and this is just 1 plus x or x plus 1. And 3 times 2 minus x. All right, so got this expression in the numerator, this expression in the denominator. Remember, I can rewrite this now as a multiplication problem. We got 3 times x plus 1 divided by 11 times 8 minus 3x times the reciprocal of this denominator thing, which is 3 times 2 minus x divided by, and then just x plus 1. And you see the x plus 1 factors canceling. And that's the problem, right? Now that those are gone, we'll have an expression that doesn't have that 0 divided by 0 form, right? So we're doing the limit as x approaches -1 of, now the numerator here is 3 times 3 times 3 is 27 times 2 minus x divided by, and then denominator is just 11 times, 8 minus 3x. And now there's something that has, this has the same value as the original expression everywhere except at -1. Up here, that this is undefined at -1, you divide it by 0. This is not undefined at -1, and so we can get our limit. Now when x is -1, 2 minus -1 is 3. 3 times 27 is 81. So I got 81 in the numerator, and then down here I have 11 times 11, 121. And there's our limit, 81 121st, which once again is probably not something you would see from a table or a graph. So 81 121st. A lot of algebra. Right, can be a little tedious, but sure you can manage. All right, now we're in this area with the Squeeze Theorem and limits of trig functions. So evaluate the limit of a trigonometric function using special limits. So here are the special limits they're talking about involving some trig functions. So one of them is the limit as, say x approaches 0. Now this could be the sine x over x, or you could flip it, x over sine x. This limit was 1. I know if you were to plug it in, it'd be 0 divided by 0, but we saw in class, I don't know if if you're not in my class, that's fine. You can just go to a table, have x gets closer and closer to 0. This expression here gets closer and closer to 1. This limit is 1. I will tell you, the sine of blah divided by blah approaches 1 as the expression in the box approaches 0. All right. These have to be the same though. All right, so what's in here must be the same in order for this thing to approach 1. So as long as the expression in here and the expression down here, or vice versa if you got this flipped around, as long as they're the same and the expression's going to 0, the value of the whole thing is approaching 1. And then the other special trig limit is the limit as x approaches 0 of 1 minus the cosine of x divided by x, or again the other way around, you could have x divided by 1 minus cosine x. This limit is 0. Actually, not the other way around, right? The other way around would be probably some kind of infinity, right? So it's got to be this way, sorry, not the other way around. This one, the reciprocal of 1 is 1, so you flip these, it's still 1. Yeah, the 0 doesn't have a good reciprocal, right? So don't flip these, right? Don't flip. All right. So anyway, you got 1 minus cosine x over x, or cosine x minus 1 over x, right? Something equivalent to this, equals 0. Again, it doesn't have to be just x in there, but as long as the expression in there and the expression down here are the same, this will approach 0 as the value of that box expression approaches 0. Okay, so these are the special trig limits that they're talking about that you'll see in the reading, see in the instruction. So the first one I'm given here, the limit as x approaches 0 of the sine of 2x divided by, and then the tangent of negative 10x. So notice those two special limits I brought up had just sine and cosine involved. So I'm going to rewrite using just sines and cosines. So this is the sine of 2x divided by, and remember tangent is sine over cosine, so this tangent of 10x is the sine of negative 10x divided by the cosine of negative 10x, which, when you divide by something, you multiply by the reciprocal. So this is the sine of 2x times the cosine of negative 10x divided by the sine of negative 10x. Okay. And then to get that special limit involved, I got the 2x inside the sine, I got the negative 10x inside the sine, so I would like 2x below this one and negative 10x above this one, right? I said you could flip them with the sine one. So I'm going to multiply the top and bottom by 2x and also by negative 10x. Sorry, that's a little tight there. So I have 2x times, negative 10x times the sine of 2x times the cosine of negative 10x in the numerator. And the same thing, I multiply by 2x times, negative 10x times the sine of negative 10x in the denominator. And then, x is approaching 0. So then this sine of 2x divided by this 2x, those are approaching 1. Since, 2x would be, if x is going to 0, 2x would be going closer to 0 as well. And then this negative 10x divided by this sine of, I should probably put these in a different color. Sorry, the blue here. So this negative 10x over this sine of negative 10x, since negative 10x, those are the same expression, and the negative 10x would be going to 0. It's going to 1 as well. So I can get rid of these, and I can get rid of these. They're both going, these fractions are going to 1. So in the rest of it, we'll stick around. Now x and x will cancel. So I end up with the limit as x goes to 0 of, negative 1/5, right? 2 up here, negative 10 down there, that's negative 1/5 times, and I still have this cosine of negative 10x in the numerator. But that's something I can actually plug 0 in, right? You can actually do a limit law here, direct substitution, one of those composite function law. So if I have x approach 0, this will approach the cosine of 0. But remember the cosine of 0, so this is negative 1/5 times the cosine of 0, but remember the cosine of 0 was 1. So this ends up being negative 1/5. Right, so that's what they're talking about with using the special limit laws, special limits with these trig functions. Now again, you can go to a table, go to a graph, graph this thing. Make sure you're in radians, by the way, right? When you're talking trig functions here in calc class, make sure you're in radian mode. Go graph this. Plug in values of x closer and closer to 0, and you'll see the output get closer and closer to negative 0.2. right, which is negative 1/5, or look at a graph and you'll be approaching a point on both sides of 0 with a y value of negative 1/5 or negative 0.2. Right, so negative 1/5 for the limit. Submit an exact answer again. You see they do all that here. All right, and show you everything I basically just showed you. I didn't write all the splitting that they're doing, but yeah. Okay. All right. So this is evaluate the limit of a function by using the squeeze theorem. All right, so I'll write out this squeeze theorem. Explain what it's saying. This is if near x equals a. Okay, so not at x equals a, but near it, right? Approaching it. You have three functions: f, which is no greater than say g, and g is no greater than h, right? So f is lower than g or equal. G is lower than h or equal, but f is not higher than g, g is not higher than h. And these two outer functions, right, the f and the h, both approach the same value near a. So the limit as x approaches a of f is the same as the limit as x approaches a of h, and say they both approach some value called L. All right. So here's a graphical thing of what's going on here. So here's x equals a, and here's the point, a comma L. So we got these functions f, so f is the lower one. So say f is approaching this location. So there's f, h is the higher one. So h is also approaching this location on both sides. There's h. Well, if both of these, the lowest function, the highest function, are approaching this point, and g is always between them, it's got to approach that point as well. All right, so this is so g could be somewhere in the middle here. That's got to be, right? It can't be it can't be lower than f, can't be higher than h near a here. Here's g. So g must be approaching that same location. And that's the conclusion of the theorem. Now then, so if all this is happening, then that middle one, right, the limit as x approaches a of g of x, must also be L. Right? Must be approaching the same location. Must be squeezed there, sandwiched. I've also seen this referred to as the sandwich theorem if you're looking it up. Okay. So in this particular problem, the function g is this half x cubed sine of x cubed minus 1 is graph below. So there's the graph of y, y equals half x cubed times the sine of x cubed minus 1. This insane graph here. Now you're asked to enter the following functions. So it says enter f below. So it's like Desmos, right? They got Desmos embedded in the assignment. So I'm entering f of x. Well, you can actually just enter the expression since it depends on only x. So negative half x cubed minus 1. And then here's h of x, positive 1/2 x cubed minus 1. So look, if I zoom in here near 0, right? It says, does the squeeze theorem apply? I'm guessing near 0, because look, if you zoom in here near 0, so you see how that red graph is between the blue and the green near x equals 0 here? And you see the blue and the green are going to the same location. They're both going to the point 0, 1, or sorry, 0, negative 1. So you see the green graph approaching 0, negative 1, the blue graph approaching 0, negative 1. So because those two are both approaching the same thing, and you see this red graph is between them, the red graph must also be approaching 0, -1. So yes, the squeeze theorem does apply, right? So the squeeze theorem applies. These two outer functions are approaching the same location, so that middle one must be approaching the same location, and that limit's -1. Oh, oh, okay. No, I know it. You can see them being squeezed in here. All right, so I know what we're on. They switched. Sorry, I didn't pay attention to that. So pay attention to that. Okay, there's a lesson for you. See how the blue and green switched here? So that does not satisfy this part. I was going to say this was the blue and this was the green, or I got red and blue here. Yeah, they must satisfy this the entire time around 0. My apologies, and that does not happen here. See how the green is lower than the blue on this side of 0, but then the green is, or sorry, then the green is higher than the blue, right? The green function gets larger. So yeah, so sorry about that. That inequality is not always satisfied. I should have paid more attention. I'm sorry. It's getting almost 2 hours here. I apologize. I started rushing my thoughts. All right, so let's scrap that. Let's try that again. Hopefully they come back to something like that again later. All right, but still, the squeeze theorem, I did state it correctly. I just, and that inequality has to hold the whole time. So on the left side and right side, the one function is below another. All right, so this is another just direct substitution. So use direct substitution. So just plugging the values in. So you just got to remember your trig values for something like this. The limit as x approaches pi over 4, 5 times the sine of -x plus 4 times the cosine of -2x. So they're telling you to directly substitute. So replace x with pi over 4. So there's 5 times the sine of -pi over 4 plus 4 times the cosine. Now -2 pi over 4 would be -pi over 2. All right, that's -2 times pi over 4. And then these are just things you should remember. Now, if you got your unit circle, if you want to write your unit circle up all the time, you can. But this would be 5 times, and then the sine of -pi over 4. Remember, that'd be the opposite of the sine of pi over 4, which is square root of 2 over 2. So this is -√2 over 2 plus, and then 4 times, and then the cosine of, -pi over 2. Remember, cosine of odd multiples of pi over 2 is 0. So this is nothing. So we end up with negative, 5√2 over 2 for the exact value of this limit. So you just got to I'm not pulling up the whole unit circle, going over all that with you. This would be -5 times the square root of 2 divided by 2. So just a direct substitution there. So more of the special limit stuff. So I had those up earlier. So this one has that 1 minus cosine blah over blah going to be involved. So I got the limit as x approaches 0. And the numerator, we got 1 minus cosine of, now the expression inside this is 5x. And then the expression down here isn't 5x, it's 6x. All right, so I need to make that 5x. Multiply by 5 over 5. And now I have, 5/6 times, and then this 1 minus cosine of 5x over 5x. Right? And the limit as x approaches 0. And then this limit here, all right, this expression here, that was 1 minus cosine of blah over blah. As blah goes to 0, right, this is going to 0. So this ends up being 0 overall anyway. This ends up being 5/6 times 0, which is 0. Right, so the limit is 0. And again, you could look at the graph of this expression. Near 0, you'll be approaching the origin, right, at some point with y equals 0. So limit is 0. And they go through all the same stuff. All right, so squeeze theorem. All right, so look, they're saying use the squeeze theorem. Right? If this is true, right, for x is between 0 and 2, so near 1, right? The limit as x approaches 1 of g. So watch, I'll even graph these, right? So I'll go to Desmos. We got y equals the opposite of the absolute value of x minus 1 plus 5. Y equals, well, I'll just put the expression in the absolute value of x minus 1 for the opposite of the absolute value of x minus 1 and then plus 5. All right, so there's this function, the left one, the lower one, and then the one on the right, the higher one. Again, just around x equals 1. They might not always be lower and higher, but near x equals 1. That's what we're doing the limit for. Limit as x approaches 1. So you see it's true for 0, between 0 and 2, so definitely near x equals 1. The other one is absolute value of x minus 1 plus 5. So the other expression, you got absolute value of x minus 1 plus 5. And you see how, and you got blue and green. You see how the blue graph is approaching this 1, 5 on both sides. So is this green graph. They're both on both sides approaching 1, 5. And what I messed up on earlier, the green is always above the blue. Right, the lower graph doesn't get higher than, it didn't switch like it did in that picture from the one I got wrong earlier. So if that's the case, the limit must be 5 then, right? This g function, right? You don't know what g is, but if g is always between these, then as x approaches 1, g must approach 5, right? Since both of these also approach 5 at x equals 1. So by the squeeze theorem, limit must be 5. All right, so another direct substitution. So again, I'm just going to say this one. So you're just plugging in, x equals pi over 3. Now the tangent of 2 pi over 3, remember tangent is sine over cosine. Sine of 2 pi over 3 would be square root of 3 over 2. Cosine of 2 pi over 3 was negative half. So this was negative root 3 over 3. Sine of 2 pi over 3 was not root 3 over 3, negative root 3. So tangent of 2 pi over 3 is negative root 3 times negative 2 would be positive 2 root 3. And then plus, and then cosine of negative pi over 3, that'd be a half. 4 times a half is 2. So I got 2 root 3 plus 2. Again, lots of stuff there. 2 times the square root of 3, though. And then plus 2. So again, just plugging in the value of pi over 3 there. There's your limit. Okay. So again, you got to get your unit circled down again if it's been a bit. All right, so okay, here we go. Let's try this again. So this is probably similar to the problem from earlier. But this time, this time we got an even power. The one I got wrong earlier had the odd power, so they switched positions. Watch this one with the even powers. They will not switch. You got so f is negative 1/2. X to the 4th minus 3. But they won't be approaching the same location. Watch, right? So 1/2 x to the 4th minus 1. So look. See the red graph, see this blue graph is approaching negative 3 on both sides of 0. The green graph is approaching negative 1. So if you look back at the squeeze theorem that I wrote again. So again, so this is happening. All right, the two functions they gave me, one is always lower than the other. That's true. But this has to happen as well. They have to be approaching the same location for the squeeze theorem to apply. See, that does not happen here, right? The higher function is approaching -1 at 0. The lower function is approaching -3 at 0. So I can't guarantee, I can't apply the squeeze theorem here, right? The squeeze does not apply because this limit of the lower function is not the same as the limit of the higher. Right. Okay, so again, just I paid a little more attention there. All right, so this one's similar. All right, so this is going to have the same issue as the one I got wrong earlier. Watch. All right, so f is this -1/2 x cubed minus 2. So there's the graph of f, this blue graph, and then h is 1/2 x cubed minus 2 also. Now you see, just like in the one I got wrong earlier, the blue graph approaches, 0, -2 from both sides. The green graph approaches that same location. Now look, the red graph is between them, but this inequality is not satisfied, right? So yeah, this thing I failed to look, I overlooked this earlier, right? The one I got wrong earlier. This has to be happening in order for the squeeze theorem to technically apply, right? So these three functions they're talking about, these two outer ones, one is never higher than the other one near x equals a. So here it's near x equals 0. So you see how, yes, they both approach the same thing, the green graph, the blue graph, but near 0 here, the green graph and blue graph switch as to which is higher, right? So on the left side of 0, the green function less than the blue. But on the right side of 0, the blue function's less than the green. So this squeeze theorem does not apply to this particular case because that inequality does not hold around 0. Right? So again, this is the one I got wrong earlier. Hopefully it makes sense why it was wrong. Again, read through the answer explanations like I did earlier. Hopefully you can figure out your mistakes. All right, so that objective with the squeeze theorem's done. All right, so then more of the just substituting. So again, I'm just gonna kind of say these, and you got to know your unit circle and junk. So the tangent of, I'm plugging in pi over 6. Now the tangent of positive pi over 6, that's the square root of 3 over 3. So this is tangent of negative pi over 6. So that's, that's going to be negative root 3 over 3. So this is negative 4 root 3. And then negative 2 pi over 6 is negative pi over 3. Now the sign of negative pi over 3 would be negative root 3 over 2, and then times the 4 would be 2. So this ends up being negative 2 root 3. So this one's negative 4 root 3 over 3. Negative 4 times the square root of 3 divided by 3. And then the next term with the plus 4 sign, negative 2 pi over 6, negative 2 pi over 3. That'd be minus 2 root 3. And just plugging in numbers, getting the values. Right? Okay. So again, I know my trig values really well, right? Hopefully you get to the point where you know them well. Now they put it all together, right? I think I've mentioned this earlier in the thing. They say submit an exact answer. As long as you submit something that's equivalent to what they got, it'll be good. All right, so another one where you're just doing a direct substitution. Now the cosine of, I'm plugging in pi over 6 here. Cosine of pi over 6 was square root of 3 over 2. And so would the cosine of negative pi over 6, where it was an even function. So this is square root of 3 over 2 times negative 3. So I'll just put that negative 3 times the square root of 3 over 2. All right, so that's for the first 2 over 2. So that's for the first term. And then minus 4 times the tangent of negative pi over 6. So again, the tangent of negative pi over 6 we saw in the last problem, that was negative root 3 over 3. So this is minus 4 times negative, so plus 4, negative times negative, so plus 4 times root 3 over 3. And again, they probably put it together, but that should be good. Yeah, I see they put it all together. But again, as long as what you're entering, if they say submit an exact answer, you enter an answer as long as it's equal to what they got. they should be taken in. And I should just have one more with those special ones, right? So yeah, I'll write this one up. Remember, you got the sine of blah, 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 sine of something over something going to 1 as that value goes to 0, and then that 1 minus cosine of something over something going to 0 as the input goes to 0. So here we got the limit as x goes to 0 of, cosecant of 7x divided by the cosecant of 3x. Remember, cosecant is 1 over sine. So this is 1 over sine 7x. This is 1 over sine 3x. And then you flip them. It'd be 1 over sine 7x in the numerator divided by, and then 1 over the sine of 3x. And divided by this is multiplied by reciprocal of this. So I can make the sine of 3x over the sine of 7x. These are the same. All right, and then to get the special limit involved, I need sine 3x over 3x. So I need a 3x down here. So I got to multiply the top and bottom by 3x and 3x. And I need sine 7x, so I need 7x up here. So multiply by a 7x and a 7x. So I have the limit as x approaches 0 of, you got this sine 3x over 3x times, and then you got this 7x over sine 7x. All right, those will be from the special ones. And then you got, so that takes care of this and this and this and this. So then you got 3x over 7x, which is just 3/7. And then this is going to 1. This is going to 1. So you got 1 times 3/7. The limit is 3/7. Sorry, that was rushed, but just trying to get that special limit involved. Over 2 hours now. I just want to get this done. 3/7. Please read through how they're using the special thing right now. All right, and then this here, this is 1. All right, so watch. I'm going to split this up. So you got this. So I'll show you how one of those special limits is used, right? This one will involve the 1 minus cosine or cosine minus 1, all divided by something, going to 0. The limit as x approaches 0. Negative 10x, minus or plus the cosine of negative 2x minus 1 divided by negative 10x. Now, if I divide through by negative 10x, divide this and this by negative 10x, this will be 1, right? Negative 10x divided by negative 10x is 1, plus, and then you have this cosine of negative 2x, minus 1 divided by negative 10x. I can make this negative 2x down here by pulling out a negative 5. So this is plus, negative 1/5. Pulling a negative 5 out of the denominator. And then you got the cosine of negative 2x, minus 1 over negative 2x. Sorry, just 5, or just pull out 5. So now I got the cosine of something, minus 1. Same thing down here. They're going to 0, so this thing's going to 0. So we got this term here be approaching 0. And then you still have the plus 1 outside here, the negative 10x over negative 10x. So the thing overall is approaching 1 plus 0. So the limit overall is 1 plus 0, which is 1. So 1. And again, you can make a table, make a graph, get that value on your own. All right, great. And that's it. Wonderful. All right, so sorry, I know I rushed that last couple, but hopefully you saw enough to help you get through this assignment on your own when you work on it when you work on it yourself. And thank you very much for watching.